Welcome to Quick MCAT Lessons, where I try to explain MCAT topics in 10 minutes or less. Today we're going to be talking about the fluid mosaic model of the plasma membrane. Imagine the membrane not as a rigid wall, but as a flexible dynamic surface, a bit like a sea of lipids with the proteins flowing in it. This is the essence of the fluid mosaic model. The primary structural element of the membrane is the phospholipid bilayer. Each phospholipid molecule has two key features, a hydrophilic or water-loving head and a hydrophobic or water-fearing tail. Now when you place them in water, they spontaneously arrange themselves so that the hydrophilic heads face outward towards the water and the hydrophobic tails tuck themselves away inside. This forms the basic bilayer structure, which is both stable and self-sealing. This is ideal for separating the internal cell environment from the outside. But it's not just lipids. Scattered throughout this bilayer are proteins, much like buoys, floating in the sea. Some of them, called integral or transmembrane proteins, span the entire membrane and are involved in transport or signaling. Others, known as peripheral proteins, sit on the surface and may interact with the cytoskeleton or act as enzymes. The mosaic part of this model refers to the patchwork of proteins, glycoproteins, and glycolipids, each with different roles and motility. Furthermore, it isn't uniform. Each section of this membrane will have a different composition depending on the needs of the cell. Now, let's talk fluidity. Unlike a solid wall, the membrane allows components to move laterally. Lipids and proteins can drift sideways within the layer, and this is what we call membrane fluidity. The degree of fluidity can be influenced by several factors. A major factor is temperature. At higher temperatures, the membrane becomes more fluid, and at very low temperatures, it can become too rigid. This is where cholesterol plays a key role. Cholesterol inserts itself in between phospholipids and acts as a buffer. It prevents the membrane from becoming too fluid at high temperatures and too rigid at low temperatures. This is like a stabilizing force that keeps things just right. Another interesting feature of this membrane is asymmetry. So there are two sides, or leaflets, of the membrane, and they are not identical. This outer layer may contain different lipids and proteins than the inner layer. For example, glycolipids and glycoproteins are usually found on the extracellular side, contributing to things like immune recognition and signaling. Because the membrane is asymmetric, certain phospholipids are found more on one leaflet than the other. This asymmetry is actively maintained by a set of enzymes. These enzymes are called flipases, flopases, and scramblases. Flipases and flopases do the reverse action of each other. Flipases move phospholipids from the outer to the inner layer, and flopases move phospholipids from the inner to the outer layer, and they both use ATP. Scramblases bring a phospholipid from the outer layer into the inner layer, and a phospholipid from the inner layer to the outer layer. This does not use ATP. An example of why this is important is phosphatidylserine. This is a lipid that normally stays in the inner layer, but if it flips to the outer leaflet, such as during apoptosis, this is a signal for macrophages to engulf the dying cell. Now let's talk about lipid rafts. These are small, specialized, and more ordered regions of the membrane. These microdomains are enriched in cholesterol, sphingolipids, and certain signaling proteins. Unlike the rest of the membrane, they are less fluid and more tightly packed. Functionally, they serve as concentrated platforms for signaling, trafficking, and even viral entry. Think of them as workstations on the membrane where key proteins are temporarily gathered to carry out important functions. So just to quickly summarize, the fluid mosaic model describes a dynamic, semi-permeable membrane made of a phospholipid bilayer with proteins embedded like mosaics. These components can move laterally, and their arrangement varies based on the cell's needs. Membrane fluidity is regulated by temperature, lipid composition, and molecules like cholesterol. And the structure isn't symmetrical. There is a functional reason behind what's placed on each side of the bilayer. That's it for this one. Next time we'll talk about membrane components.